So today we're going to start the proof of the cone theorems. So let me remind us of the specific theorems. Well, the ones that we're going to talk about today. So we have the non-vanishing theorem. So let's say that x is projective, d is Neff. So let's say it's a Neff Cartier divisor, and g is a Q divisor. Such that one AD plus G minus K is big enough. In particular, that we're assuming here that it's Q Cartier. And two, let's suppose that the pair x comma minus g is KLT. Then for m very large, we have that H0 MD plus the roundup of G has sections. Okay, so that was the non-vanishing theorem. Are there any questions about the statement? Okay, and then the basepoint free theorem. So suppose x is projective, and let's say x comma delta is a KLT pair with delta effective. So delta is a boundary. And let's say D is a Neff Cartier divisor. Such that AD minus KX plus delta is big enough for some A. So again, implicit in that is that it's Q Cartier, but of course here it's true because x comma delta is assumed to be KLT, so it's not really an assumption. Here it was really a condition on our choice of G. Then AD minus KX plus delta is big enough for some A. Then D is semi-ample, i.e. some large enough multiple is basepoint free. Okay, so that's the basepoint free theorem. And then last time we also stated the rationality theorem and the cone theorem. I won't restate those today because we won't prove them today. But I wanted to say kind of a very brief outline of the interrelation between these theorems. So the idea is that non-vanishing implies the basepoint free theorem, which implies rationality, which then implies the cone theorems. And then really, I guess I can say that, and then basepoint, once you have the cone theorems, then basepoint, the cone theorem, then basepoint free plus cone implies contraction. Okay, and the strategy for non-vanishing, base point freeness, and rationality is all essentially the same. So we're going to talk about the general strategy first, and the idea is to induct on the dimension, and then when we have some pair, we want to find some divisor f on it, such that when we restrict that divisor, we can apply our non-vanishing base point free theorems to that divisor, and then use some vanishing to lift sections and get it by induction on X. So here's kind of the ideal situation. So let's say, just for simplicity, that X is smooth. And let's say we don't have a boundary right now, just for the general strategy, just to make the notation a little better. And so suppose that we have a situation where M is some ample divisor, and F is some effective divisor, say integral. Then we can look at the exact sequence 0 to OX KX plus M. Then we twist up by F. And then we restrict. So then by junction, when we restrict, here we get KF, because KX plus F restricted to F is KF. And then we have M restricted to F. Okay, so in this very nice case, we have this exact sequence, and now by Kodaira vanishing, well, then we know that H1 of Kx plus M is 0, so that tells us that the map on sections that's given by restriction is surjective. So in this very nice situation, then we can apply our inductive hypothesis to F with the divisor M and lift sections to produce sections either for non-vanishing or for base point freeness. Both of those are statements about existence of sections. So we can use this exact sequence to lift sections. So in particular, what do we want to lift sections of? Well, we want to lift sections of our divisor B times D for the base point free theorem. So let's say for now, it's going to be the same strategy either way, but let's stick to the case that let's assume we're trying to prove the base point free theorem. Otherwise, we have to modify this a little bit, because in the non-vanishing we had this multiple of D plus this roundup of G, but still going to be the same idea. But for simplicity, so we want to lift sections to produce sections for BD, but BD is, well, BD minus KX is assumed to be well, let's say we can write BD minus KX in the form. So yeah, let me say it this way. If we can write BD minus KX like this, and here I really want equality, then we can apply this strategy to lift sections from the restriction to F to sections of BD. And this shouldn't be too far off from the truth, because our assumption is that BD minus KX is big enough. So it's going to be ample plus effective, but maybe things aren't Cartier. Maybe you need rational coefficients here. Maybe the singularities are bad. Maybe F isn't irreducible. So we need to kind of modify the situation so that we can actually write an equality like this. Also, this big enough is or like big being ample plus effective is like a numerical statement. So we need to mess around with the situation so that we can apply this strategy. So that's the basic idea. But we also have a little more flexibility because we don't really need M to be ample. What we need is that comma out of Vivek vanishing holds. For whatever we put here at the beginning. Okay, so the first observation to carrying this out is that we can resolve and work on a resolution as long as we kind of add the right divisors everywhere. But the fact that on this resolution we have this flexibility to add divisors lets us actually carry this out. So observation 1, let's take really any proper birational map, but let's just say it's some, I guess above I assumed X was smooth, but in general X won't be smooth. So take some proper birational F. Then if we write down the pullback of D plus any divisor E where E is effective and F exceptional, then by this fact that we've used a couple of times in the class, we know that H0 on X, OX, BD is the same as H0 on Y, OY, BF upper star D, but the important point is it's the same as H0 on Y, OY, BF upper star D plus RE. So we have this flexibility to add some exceptionals for this resolution to get an expression of the form thing we want minus kx is equal to something where we have a piece that we can apply comma out of vanishing and then a piece f that we can induct with. Okay, so let's write down exactly what we need then in this setting upstairs. So if we can write down b f upper star d minus ky as n plus delta y. So I'll again say want to write down bf upper star d minus ky of the form n plus delta y plus f minus e, where we want n to be big enough. We want this delta y to be some KLT boundary. So now n plus delta y will satisfy comma out of Vivek vanishing. That cohomology of ky plus n plus delta y will vanish, or cohomology of anything numerically equivalent to that will vanish. And then f, we want this to be some irreducible divisor where we can induct. So we want this to be irreducible, but we also want to know that when we take n plus delta y restricted to f, we want this to be something that we can apply our hypothesis to on f. So we need this to be of the form nf plus delta f, where this is some KLT boundary for f, and then where nf satisfies the hypotheses. So ideally that it's big enough, or actually we're going to get it so it's even ample. And so the important point is this condition that we want the restriction of delta y on f to be a KLT boundary for f. So we need that f doesn't share any components with delta y because we can't really control the self-intersection of f. But let's assume like this map, we said it's anything proper birational, but we can choose it, like we can keep resolving until all of these divisors are S and C. And so really what that amounts to is saying that f doesn't share any components with delta y, because then if I take this S and C divisor, delta y that doesn't share any components with f, and then when I restrict it, I'll get some S and C divisor with coefficients between 0 and 1, but strictly less than 1 by that assumption. So really we need that that f and delta y don't share coefficients, and then finally we want this to be f exceptional and effective. So we want E to be f exceptional and effective, so that then when we add it over, it doesn't change. It doesn't change the sections. Okay, so that's what we're looking for. Or maybe it's not if and only if, but in particular, we're necessitating that f is not contained in the support of delta y. Okay, so that's our first observation, that if we can find some resolution, some proper birational map, and some divisors where all of these things are true, then we can apply our inductive idea to this setting to get that we have sections for B F upper star D plus E, but then because E is effective exceptional, then those are the same as sections for BD downstairs on X. Now observation 2 is that we have some more flexibility, because if we're resolving anyway, we might as well resolve until our linear series we care about is easier to understand. In particular, let's assume that F upper star MD is of the form L plus some RJ EJ plus some of RK FK, where this L is some base point free linear series. So this is the moving part, and we can resolve until it's base point free. And then this is the fixed part, but I've just broken it up into the whatever exceptional pieces, and then these pieces are not F exceptional. So basically, downstairs we have our linear series MD, and we want to show it's base point free. So we write it as some moving part plus some fixed part, and then we blow up to resolve the base points of the moving part, and the strict transform there gets us L. So now L has no base points and it moves around, so it's base point free. And then whatever we have left, when we pull back, we just incorporate that into this these E's and these F's. And the F's will come from whatever, if we had some divisorial loci in our base locus downstairs, then when we pull back, we'll get these F's that are not exceptional, but are still in the base locus. And then the E's will be exceptional divisors lying over higher codimension pieces of the base locus. But the other observation is that when we do this, these R's are all greater than 0. And so in this linear combination, in the thing we want in the end, so now we're saying let's keep blowing up until we have this decomposition for D. But in this combination, we have this KY, and in the KY we want to relate KY to KX downstairs, so we're going to have discrepancies in this expression, and those discrepancies are only going to be attached to these E's. And then we'll have some other pieces that are these non-exceptional RKFKs. And so the only reason that I wrote it down as like the reason we want to keep track of which which are exceptional and which are not, is that for the exceptionals, that's where we have actual discrepancies, so that in this linear combination upstairs, this BF upper star D minus KY, we'll actually have like some combination of R's and discrepancies in front of the E's, but then we'll only have R's in front of the F's. But then later when we apply this argument, we're just going to kind of combine all of this into some sum of RKFKs, where some of them are exceptional and some of them are not, and we're just going to keep track of, well, if they're exceptional, this tells you something about the R's and the A's, and if they're not exceptional, it tells you something else about the R's and the A's, where the A's are discrepancies. But for now, I wanted to really split it up so we see the different behavior between the exceptionals and the non-exceptional pieces. So, okay, so now we're going to find some linear combination that satisfies this requirement. So let's write BF upper star D minus KY equals, okay, so we want to pick for n and delta and f and e, we want to pick divisors that we have some control over. So we have to think, what divisors do we know anything about? So we know that AD minus KX is big NF. So that's big NF on X. That's our assumption. So if we pull it back, this is still big NF because F is birational. So that's some piece that we know something about. So if we can write BF upper star D minus KY in an expression that involves this, then okay, we're part of the way there. We have a big NF piece. But once we add this F upper star A, we need to write down the difference between the BF upper star D and F upper star A. So we have B minus A F upper star D. And now we want to involve this L, because this L is another piece we know is base point free. So we should feel free to add this L that we want. So let's just add that. So maybe we have to add some multiple of L. But now to balance this out, so we actually get an equality, we need to then subtract C times M from this F upper star D, because F upper star MD is L plus other stuff. So kind of to have any hope of this equality, we want to subtract that out. And now we need to see what's left over with these E's and these F's. Okay, so what's left over? Well, we've added L. Let me make sure I get this right. So let me do the K first, actually. So we've added F upper star KX. And what I didn't do is write down the discrepancies. So we don't have a boundary on Y, so we just have discrepancies like this. EI, where these are exceptionals. Or maybe I should use J, so I have the same indexing as I did up here. So we have this AJ, EJ. And so on one side we have minus KY. On the other side we have the minus KX. So to balance it out, we need to add minus sum of AJ, EJ. And now we need to just take care of the extra contribution on L, coming from the fact that we balanced out adding CL with subtracting C times MD. So we have to carry the rest of these expression, the rest of these E's and these F's in this expression for MD, and so that becomes plus C times the sum of these RJ EJs and plus C times the sum of these RK FKs. Okay, so here's our expression for BF upper star D minus KY in terms of these divisors that we know something about. And now our observation is that if C is greater than or equal to 0, and if this coefficient here in front of F upper star D is non-negative, so if B is greater than CM plus A, then we have that this piece is Nef, because in the hypothesis of the base point free theorem, D is Nef. So then this piece is Nef, and also this piece is base point free, and in particular Nef. And so we've written things in terms of a Nef divisor, a sum of a Nef divisor, a base point free divisor, a big Nef divisor, and then some exceptionals and some Fs where we can hope to control these E's and these Fs. And so we're just going to absorb all of this stuff into our big Nef divisor N. And if you think about it, this depends. So A is fixed. A is in the hypothesis of the theorem, but B and so A is fixed. M is also fixed because here we're picking an M. Well, I haven't said how we pick M, but once we fix M, then we write our pullback like this. So let's say M is fixed as well. And the things that we're really allowed to vary here are B and C. So we have this N that's big enough. That's this combination, and then we have to study what's left. Okay. So if we just put this stuff together, what's left? We have sum of CRJ minus AJ times exceptionals plus plus sum of CRK times FK. And what do we want for this last piece? Well, if we scroll back up, we have our big NF guy, our N. So this last piece, this sum here, we want this to be our KLT boundary plus some irreducible integral divisor minus some exceptional effective divisor. So this we want to be delta y plus f minus e, where each of these components are as above. And here, what do we have flexibility to choose? We have flexibility to choose the c in this expression. So R and A's are determined by the resolution and by the particular multiple of D that we picked, but we have the flexibility to pick whatever C we want. So how do we get this to be true? We pick C such that the maximum of CRJ minus AJ and CRK is equal to 1. Or how we'll actually see it, just because when we actually run the argument, like I find it easier to think about it this way, but when we actually run the argument, there's a negative sign everywhere. And that's essentially because when we run the argument, this delta will be absorbed into the boundary. And so what's left over are the discrepancies, but the discrepancies have minus the coefficient of the boundary. And so another way to say this is that we're looking for the minimum, and this is how it'll actually appear, of the negatives to be minus 1. Okay. So if we pick such a C, and let's just call this whole divisor B of C, depends on our C. So we fix the C that makes this true. Note that these R's are non-negative because they come from pulling back this MD. And these A's, well, these A's are discrepancies, so we have a bound on them. Yeah. Okay, so we pick such a C where we get exactly this 1, some components with coefficient 1 and everything else with coefficient strictly less. And then we let F just be the round down of B of C. Now that's some integral divisor with coefficients exactly 1. So it's some reduced integral divisor. And now what's left over? Well, whatever's left over, let's just write it as delta y minus e, where we've just split it up into the positive terms, the negative terms. So where both delta y and e are effective. So let's write it that way and then check that that this delta y and this e satisfy the conditions that we wanted. So the conditions that we wanted are that delta y is a KLT boundary. Because we've assumed we've blown up until everything's simple normal crossings, that just means that delta y has coefficients between 0 and strictly less than 1. And then we need e to be effective and exceptional. Okay, so let's check that this is satisfied. So here we picked our c so that the max of these coefficients of the e's and the f's is 1. So we know that everything else here has coefficients strictly less than 1. So we have so this delta y, this piece that's, because we wrote it as effective minus effective. So whatever the positive coefficients are, they're strictly less than 1. So that tells us that it's the KLT boundary. So I'll say since the round down of b of c minus the round down is less than or equal to 0, then that tells us that delta y is a KLT boundary. So there we're good. And now what's left over, we have to show that whatever is left over is exceptional. That it's minus exceptional. So what's left over? What's left over is exactly all the components of b whose coefficients are negative. So minus e equals a sum over c rj minus aj being less than or equal to 0 of crj minus aj ej plus, well, I guess that's it. Because if we scroll back up, these r's are non-negative. So these r's are always going to contribute to the delta piece or the f piece. They can't contribute to the e to the minus e piece. So whatever's left here is the sum of these, but I mean, just from looking at it, this is exceptional. Okay, so we've written this b divisor as a KLT boundary plus an integral divisor minus an effective exceptional divisor. And so we've written the whole thing as a big NF divisor plus our KLT boundary plus our integral divisor minus an f exceptional. There's an issue here. Well, there's really two issues. So issue 1, and they're both kind of fixed in the same way. Well, okay, let me actually just rewrite what we just said. So now we've written b f upper star d minus ky as n plus delta y plus f minus e, where n is big enough. This is a KLT boundary. This is integral, and this is effective and exceptional. One thing I didn't check, but which is true, is that the component f doesn't share any components with delta. And if we go up here, that's essentially true because the way we constructed it is by taking this divisor and splitting it up, this b divisor, in terms of what the different coefficients are. So all the e's and the f's here don't share any components. So like the ej's and the fk's don't share components. So when we split it up in terms of things with coefficient exactly 1, things with coefficient less than 1 but bigger than 0, and then things with coefficient strictly less than 0, then there's no components shared between them. So this is integral, and f is not contained in the support of delta y. But our two issues are that one, f is not irreducible. So in particular, f might have self-intersection. It might not. Well, it doesn't have self-intersection because everything's S and C, but it might be multiple components that intersect. So in particular, f isn't normal. And two, we don't really have control over n restricted to f. This n restricted to f doesn't have to satisfy the hypotheses of the statement we want to prove. And so the solution is that we perturb everything by adding some sum of pj fj's to make f irreducible and n ample. So basically, if we look here, what goes wrong is there might be multiple components that achieve this maximum of 1. But if we start perturbing something by just some small coefficients in this b divisor, then we can perturb it so that when we hit this maximum, there's exactly a unique component that hits the maximum. And then similarly, we can use this kind of negativity lemma ideas and big NF ideas that came up in a proof in the proof of one of the steps in Kamada-Vivek vanishing to perturb things so that this big NF piece is actually ample because we've like added some minus exceptional, like minus epsilon exceptionals to it. Okay, so that's the strategy, and now we need to carry it out for to actually prove these theorems. Any questions about that? Okay, so for today, I'm hoping to get through proving that non-vanishing implies the basepoint free theorem using this argument. And then again, this argument is still what applies to prove the non-vanishing theorem. It's just a little more delicate than this piece. So right now we want to prove that non-vanishing implies basepoint free. Okay, so our setup again is that D is Nef, X comma delta is a projective KLT pair, and AD minus KX plus delta is big enough for some A, and we're going to just fix an A in this proof. And we want to show that D is semi-ample. And of course, so the other issue with this outline is that here we didn't have a boundary on X, but the only reason we didn't do that is to kind of simplify the notation. But now we actually need to include an extra divisor delta coming from X, which is why I labeled this other one delta Y. Okay, so step one is that non-vanishing implies that MD has some sections. Okay, so let's go back and see what non-vanishing says. So non-vanishing says that we can produce sections for these divisors of the form MD plus the roundup of some G, where minus G is some KLT boundary, and where this assumption is satisfied for the KLT pair X comma minus G. So we can't apply it directly to our pair X comma delta because we want MD to have sections not MD plus our boundary or plus the roundup of our boundary. So we need to apply this kind of resolution argument to tweak things around to produce sections for MD itself. So in particular, we want this G that we're gonna apply the non-vanishing theorem to be exceptional for some birational map, because we saw that doesn't change sections. So just like before, we're gonna take some f from y to x, a log resolution, and now such that this is just basically the definition of KLT, such that we write f upper star kx plus delta plus sum of aj fj, and now we have a delta, so not all of these f's are exceptional anymore, and so that's why we're now including like what I called e's and f's before in this expression, where I broke it up into exceptionals and non-exceptionals, because in the case of no boundary, the discrepancies are only on exceptionals. Now we don't have that anymore, so now this is just going to run over all our possibly non-exceptional divisors that appear in this discrepancy. And in fact, some of these will even have being 0 because we're going to have some f's later that come from this base point freeness equation on MD. So even some of these will allow to be 0. But what we know is that AJ is greater than -1 by the KLT condition. And then 2, we'll write f upper star AD minus KX plus delta minus the sum of PJ FJ. So we're going to pick a resolution where we can write an expression like this, where this is ample for these p's small enough. And here's where our perturbation is coming up. And why can we do this? Well, this is the argument that we already gave. This boils down to this fact that that because AD minus KX plus delta is big enough, then we have this stronger form of Kodaire's lemma that says that we can write it as AK plus 1 over Kn, where this is effective, but doesn't depend on K, it's just a fixed effective, and this is ample. And so we just resolve further. We pick our f so that our f also resolves this n piece. And then when we pull back, we get the pullback of an ample plus some effective piece that with small coefficients, because we have this 1 over k that doesn't depend on the resolution, we get to pick it. And so if we subtract some small epsilon exceptionals, then our pullback of ample minus these epsilon exceptionals becomes ample, and then whatever we have left over is going to be the strict transform of these n's, but that comes with really small coefficient, and so again it fits into this this minus sum of PJ FJ, where PJ is very small. Okay, so that's how we can write it this way. So we need to resolve further, so this n is also log resolved. And this gives us our perturbation that makes things work. So now we already said kind of one of the things we needed our perturbation to do is make this n still remain big enough when we restrict it. But now we're perturbed, so actually this n is going to end up being ample, and ample divisors are preserved by like the property of being ample is preserved under restriction. So now that we have some ampleness instead of just big NF in our n, then 2 will be fine. But also because we got to pick the p's, we'll make 1 be fine as well, because here we can pick any p's that are small enough. Okay. And in fact, later we'll have to kind of wiggle the p's around some more, depending on what other coefficients appear. Okay, so let's write down now this whole divisor. So our ample, let's rewrite it as A times F upper star D plus, so now we use our 1, so we use our discrepancies. So since I'm subtracting kx plus delta, I can replace that by subtracting ky and then subtracting the discrepancies. Sorry, adding the discrepancies because they're on the other side. So plus the discrepancies sum of aj minus pj, because now we have these minus sums of pj in our expression that we're writing down, and then yeah, that's it. So now we're just gonna call this G. And this is why here we're allowing some of the A's to be 0, because it might be that the PJFJs that appear in this in making this difference ample, those are going to include the strict transforms of n, and the strict transform of n might have nothing to do with the boundary or the exceptionals, and so those will appear with coefficient 0 in this sum of AJFJ. But that's okay. Okay, so we'll call this G. And now what do we know about G? Well, we know that AJ minus PJ is greater than -1, because AJ is greater than -1 and these P's are infinitesimally small. So that implies that the roundup of G is effective. But now the other claim is actually, it's not just effective, but it's exceptional. So what does it mean? Like, which components live in this roundup? They're exactly the components where AJ minus PJ is greater than or equal to 0. I guess it's strictly greater than, because if it's 0, it's not there anyway. So the components that appear in this roundup if and only if this AJ is positive, but AJ was the log, or was the discrepancy. And which divisors have, like, if I have a divisor with positive discrepancy, it has to be exceptional, because the divisors with non-zero coefficient in our discrepancy are minus the divisors in delta, and then like minus the coefficients times the divisors in delta, plus whatever comes from exceptionals, but delta is effective. So this is where our assumption that delta is effective comes in. So since delta is effective, any of the components that appear in the discrepancy divisor with non-zero and strictly greater than 0 coefficient have to be exceptional. Okay, so we have this roundup of G that's effective and it's exceptional, and now that's what we're going to use as the G in our non-vanishing theorem. So right, so then H0 on Y of an expression like this is equal to H0 on X of MD, because this roundup is effective and exceptional, but on the other hand, this is not equal to 0 by non-vanishing, because well, what were the exact assumptions we needed? Well, it's exactly what we had here. So I'm just gonna move that down. It's exactly what we had there. That AF upper star D plus G minus KY is big enough. That's exactly the assumption for the non-vanishing theorem, and that's true because in fact it's ample. It's not just big enough. We chose everything, so it's ample. Okay, so that's step one, assuming non-vanishing. So now step two. Now, since MD is not empty for M large, now we can actually consider its linear series. It's a non-empty divisor, and we want to show that it's base point free for large enough M. So we actually want to look at what's called the stable base locus. Which is defined as the intersection over all M of the base locus of the linear series MD. And a fact about the stable base locus is that eventually it stabilizes. Also, I should say this is a set theoretic intersection. This stabilization is not true scheme theoretically. But set theoretically, this is equal to the base locus of MD for some M large enough, and that's a Noetherian induction argument, which you can find, for example, in the Positivity book by Lazarsfeld. Right. So now we fix this M. So step one, use non-vanishing to show that there exists some M where we have sections. Once we have sections, then we can take a large enough M so that this base locus is stabilized. And now what we want to show is that this base locus is empty, because that will tell us that it's base point free for a large enough M. So let's suppose otherwise. So let's suppose that the base locus of this large enough M where everything's stabilized is not empty. Now we can use this particular M to write down, to pick our log resolution as we wanted to in our strategy. So now we pick a log resolution. Satisfying satisfying what we wrote down above, 1 plus 2 from step 1. as well as this base point freeness condition. I'll call it 3. Okay, now we can do this because we have sections. So we have a linear series. I don't know why the screen share keeps cutting off the bottom. So like this is the bottom of the screen for me. So sorry if things are getting hard to read at the bottom. I'm trying to keep an eye on the on my computer to make sure that doesn't happen. But okay, so now the observation is that when you impose property 3 on your resolution, then you actually have that the preimage of the base locus of MD, at least set theoretically, is equal to the base locus of F upper star MD as sets, and the base locus downstairs is equal to the union of the images of these FJs. But again, because we keep writing this expression where we have all the Fs that have appeared. So some of these Fs might appear with coefficient 0 because they have nothing to do with the base locus of our divisor, but they have to do with the discrepancies and the n in the big NF assumption. So we want to write, just to make everything uniform in our notation, we'll write the union of F of Fj such that Rj is strictly greater than 0. Where here Rj is greater than or equal to 0, just so we're summing over the same set of divisors. Okay, so now we're going to find a contradiction by our inductive argument. So we're going to prove by contradiction. We'll find an Fk with Rk strictly bigger than 0, such that Fk is not contained in the base locus. And that'll be a contradiction. And the way we're going to do this is by picking this Fk like we wanted to in our strategy, and then restricting to the Fk, producing sections on the Fk by non-vanishing. But then as soon as we have sections downstairs, then whatever their vanishing is, if it's a non-zero section, it has to be a subset that's strictly smaller than Fk. And so as long as we can lift those sections using common of Vivek vanishing, then we get a section on X that doesn't vanish identically on all of Fk. And so that by definition means that F can't be in the base locus. So that's going to be our contradiction. Any questions at that point? Okay, so now we'll write down the appropriate divisors for our strategy. So that we have this n, just like before. And it was b times f upper star d minus ky plus the sum of aj minus c rj minus pj. So now the difference is that we have this this extra perturbation by these p's. But just like before, now we can write this as numerically equivalent to b minus cm minus a times f upper star d plus c times rl, our base point free piece. So that's why we have this b f upper star d as well as this minus c rj, because that's the difference between L and f upper star d. So we have this plus CL, just like before, and then plus the piece coming from our discrepancies, which was this piece. So this is exactly like what we wrote down in the strategy, except we have this extra perturbation by these p's. And now the upshot is that this is big in Neff. This is base point free, so in particular it's Neff. And this is ample by the choice of our p's. As long as the coefficients are non-negative, so as long, or strictly positive, I guess. As long as, let's say C is bigger than 0 and B is greater than or equal to Cm plus A. Okay. And so that we've produced this divisor that depends on B and depends on C. But that's as long as we're in this range where C is greater than 0 and B is greater than or equal to Cm plus A, then our divisor end is ample. And that was the strategy that we outlined above. So now we write down the roundup of this n. And here we have to look at this expression. So bf upper star d minus ky is an integral divisor. So we're just rounding up these aj minus crj minus pj pieces. So this roundup is a f upper star d minus ky plus the roundup of aj minus crj minus pj fj. And now we pick right. We pick our p's and C such that, just like in our strategy, such that the minimum of these coefficients, aj minus crj minus pj, and notice here now I have a minimum because this is minus what we had when we wrote down the strategy, is -1, and this is achieved for a unique index. Now we have these p's, these very small p's that we have floating around, so we can make this be achieved for a single f. And so now we have that this sum of aj minus crj minus pj fj, we can write it as we have this one piece f equals fk, which is our unique index that hits exactly -1. So we have a minus f, where f is an integral divisor. And then just like before, we have some other piece, which we can write as, now because we're minus everything we had before, we can write this as E minus delta Y, where this is effective exceptional, and this is the KLT boundary. So this is exactly like before, except now that we have these p's in there, we have guaranteed that that f is irreducible. But in particular, because f is integral, then in this roundup over here, we're just rounding up the a piece. So this is the same as the roundup of a plus, minus our f, because f came with coefficient -1. Okay. So now we're just gonna use vanishing to lift our sections and check our inductive hypothesis. So step 4, the induction on dimension. All right, I guess it's not really an induction, but we're applying, let me just call it lifting. we're applying our non-vanishing to something lower dimensional. Okay, so now we go back all the way over here. What was n? Well, n was now in our new notation. It was defined by ky plus n is equal to bf upper star d plus a minus f. So ky plus the roundup. Well, yeah, let me just round up everything. So then ky plus the roundup of n is equivalent to b f upper star d plus the roundup of a minus f. That's what we got by putting together our equalities. So now we'll write down our twisting exact sequence for this f. So 0 goes to oy of bf upper star d minus plus the roundup of a minus f goes to oy bf upper star d plus a plus the roundup of a goes to o f of the restriction goes to 0. And now this term is linearly equivalent or numerically equivalent to ky plus the roundup of an ample. And so its h1 is 0 by one of the forms of Kalmata-Vivek vanishing. I gave this weirdly written form that was exactly equivalent to the ample plus boundary version. But yeah, so h1 of this thing is 0 by Kalmata-Vivek. So that tells us that this map is surjective on global sections. This stuff restricted to f minus the canonical of f. We want to check the assumptions of non-vanishing. So G will be this roundup of a restricted to f. So this whole thing is equal to, well, by adjunction, this kf is like kx plus f restricted to f. So this is bf upper star d plus a minus kx minus f restricted to f. But this was n, which is ample. So then taking G to be the roundup of, or really just to be A, I guess. Restricted to F. I'll round up. Then we get non-vanishing on F. So we get that this is not 0. And so we have some non-zero section there, which by surjectivity lifts to some non-zero section of bf upper star d plus a. Okay, and we're like 2 seconds away from the end, so I know I'm a minute over, but I'm going to finish. So what do we have now? So we've picked a non-zero section of bf upper star d plus the roundup of a, such that when you restrict it to f, it's still not 0. And remember, f was this component of the stable base locus of BF upper star D. And now the issue is that we have this plus A. So the last observation is that the roundup of A is actually exceptional, and this was just like before. So it's effective. We know it's effective, and it's exceptional as well, just like before, because the only coefficients that appear with the only divisors that are going to appear with coefficient strictly bigger than 0 are the exceptionals, because those are the ones that could possibly have discrepancy bigger than 0. So whatever this roundup of A is, it's actually exceptional. And so this is the same as H0 on X of BD. And so we found some section of B times D for an arbitrarily large B, right? This N of BC, we said this is true for any B and C that satisfy these inequalities, that C is greater than 0 and B is greater than CM plus whatever it was. So this is effective exceptional. So we found some section of BD that when you pull back is not identically 0 on all of FK. And that's a contradiction, because that implies that FK, well, that implies that the image of FK is not contained in the base locus of BD for all large B. But that contradicts our construction of FK, because our FK was a component of the stable base locus of the pullback. So that tells us that our series is basepoint free, and that's the end of non-vanishing implies basepoint freeness.